Hello, and welcome back. We've been talking a lot about this idea of momentum, a description of motion, and how impulse, a description of interactions, changes the momentum, the description of impulse. In this video, I wanted to take some time to dive into a couple of example problems and specifically lay out my thought process when I approach these types of problems. So let's go ahead and let's get to it. So in this first problem, we read it that a car has a mass of 2,000 kilograms and is moving with a constant velocity of 10 meters per second due east. The question is, what is the momentum? Now, whenever I solve problems, I like to start by drawing a picture. So here we have a car, and I'm going to draw it moving eastwards, and it's moving eastwards at 10 meters per second. Now, why do I do that? I do that because it gives me a very clear and defined picture of the direction. The direction matters a great deal because the direction tells us whether our vector is positive or negative. And yeah, here we're just dealing with a car that's moving, not a very complex problem. But when we start to get to those more complex problems that involve collisions and those types of things, it really makes a difference to have a well-defined direction. And the picture just helps cement that in our mind. Alright, well, I also like to take the time to really write out my known values and my unknown values, or to mark them off, right? And here we have two known values. We have 2,000 kilograms, that is the mass. And we have the velocity as well. We have the velocity, which is a vector quantity, is 10 meters per second in the positive I-hat direction. Yeah, we're back to dealing with vectors. So we have the magnitude and direction of the velocity. We have the mass. We know those two in its entirety. Now we ask for the unknown, or what are we looking for? The thing that we're looking for here is going to be the momentum. And knowing that we're looking for the momentum informs us about what related or relevant formula we might need. And here the relevant formula is that the momentum is the mass times velocity. It's just a definition equation. So we know what the mass is, that is 2,000 kilograms. We know what the velocity is. The velocity is 10 meters per second in the I-hat direction. So what is our momentum? Well, our momentum would therefore be equal to 20,000 kilogram meters per second in the I-hat direction. That gives us our full momentum vector. Again, an easy problem to start us out, but just sort of defining the path that I would normally take, where I draw out a picture, identify some knowns and some unknown values, figure out what formula I need, apply those formula, and then it's often helpful to check that we do have the right units, and the unit of momentum is a kilogram meter per second, so that checks out. So we take this and we say, okay, well, what can we do with momentum? We can look at problems in which our momentum becomes a little more complex. Our system is a little more complex. And here we're dealing with a system that is a bunch of raindrops, right? So our system here is multiple objects, multiple raindrops. We draw a picture. Here's the ground. We know the ground is going to be some area of land that the rain is falling on. We look at the rain and we say, okay, well, I'll draw a picture of some clouds here. The clouds are dropping rain onto this area. And the question is, what is the momentum of the rain? So we are asking, what is the momentum of multiple objects in a system? When we take a look at this system, well, the system is going to be comprised of all of the raindrops that are present. So we take the time to calculate every single raindrop's momentum, and we can find the total momentum of a system by summing together the momentum of the individual raindrops here. So I'll use pi, where I is equal to 1 to the n number of raindrops that are present, but that's unrealistic. You can't really calculate all of the raindrops' individual momentum. So we have this idea sort of what we're going to do, but we read through the problem and it gives us some insight. It tells us that rain hits the ground at 10 meters per second. This is the terminal velocity of rain. So what this means is that when we take a look at our total momentum, well, yeah, it's going to be the mass of one raindrop times the velocity of that raindrop plus the mass of a second raindrop times the velocity of the second raindrop. And so on and so forth. Third, fourth, fifth, 578th raindrop, however many. But what's nice here is that all of their velocities are going to be the same. All of their velocities are the terminal velocity. So what we can do is rewrite this as the sum of the masses. And we take the sum of the masses and we multiply it by the velocity of the raindrops, the 10 meters per second. And this term right here ends up just being the total mass of all of the raindrops. So we probably could have figured this out sort of empirically, but what we're really looking for is the total mass multiplied by this 10 meter per second velocity. So if we find the total mass of all of these raindrops, then we can figure out the velocity. Well, we look at the problem again and we see that the problem tells us that we have 1 centimeter depth of water that hits the ground. 1 centimeter of rain hits the ground. And we are given a 10 square kilometer area. With that, we could actually figure out the volume. How do we find the volume? Well, the volume is area multiplied by height. So we're starting to get an idea of how to solve this problem, because if you know the volume, then we go back to this idea of density, where density is mass times volume. I'll use a big V here. Oh, I should not have written a vector arrow there. I'm going to use a capital V here to represent volume, which is area times height. And we know the density of water. The density of water is just 1 gram per centimeter cubed, or 1,000 kilograms per meter cubed. If we know the volume, then we can figure out the mass. If we know the mass, we know the velocity, we can figure out the momentum. Okay, so we got a game plan then. We walk through this process, just kind of throwing things at the wall, seeing what gets us to a reasonable location. We find a starting point. We then begin to plug things in to figure out what are these values. So instituting the sort of plan that we have, we take this momentum relationship and we can rewrite it. That the momentum is, that the mass is the density divided by the volume. Well, the volume was area times height, so we can actually write this as the density divided by the area times height, where the area is your 10 kilometers squared and your height is 1 centimeter. All right, well, that's the total mass of the volume of water that's hitting the ground, the total mass of all of the rain that hits the ground. So that means that the momentum, the momentum P is equal to the density of water, rho, divided by the area and height multiplied together. And we multiply this by the velocity that our water hits the ground at. A couple of notes here are density in base SI units for water is 1,000 kilograms per meter cubed. That is the density that we're using here. You will need to convert all of your distances from centimeters to 0.01 meters, kilometers to meters as well. 1,000 meters is a kilometer. And when you do all of that, you would find a momentum. Momentum equal to 2,000. Hold on, let me get this right. 1, 2, 3, 4, 5. 277,777 point, and technically 7's all the way down, kilogram meter per second squared. But hold on, that is way too many significant figures, right? If we go back to our significant figures, 1, 10, 10, those are all one significant figure, and that's because we don't know these values actually very accurately at all. When we typically measure rain, we don't know that level of accuracy. So really what we would probably write is 300,000 kilogram meter per second, or 3 times 10 to the 5, right? So that gives us our momentum of our rain. And you ask about the direction. The direction is going to be downwards minus j hat for our velocity, which is 10 meters per second in the negative j hat direction. That is our end result. And I'll put my minus j hat in earlier. Okay. So a little more complex problem. Why is it more complex? Because we are defining our system to involve multiple objects here, in this case multiple raindrops. When we find the momentum of multiple raindrops, it's just the summation of the individual raindrops. And here every raindrop has the same speed, so it's just basically the total mass multiplied by velocity. And you go through, you find that mass, you can solve the problem. So this involves objects falling with constant velocity, but what happens when velocity changes? This is when we start dealing with the impulse momentum theory. The idea that your impulse is equal to your change in momentum. So in the next problem, what we're going to look at is the final speed of a rugby player that collides with a goalpost. We have a defined system being the rugby player. The goalpost is going to be exerting a force on the rugby player. And we are going to see what the final velocity of the rugby player is given a force and a distance. So, like always, I draw a picture, right? And I'm not particularly great at drawing pictures, but here's my rugby player holding a rugby ball. This rugby player is going to collide with a goalpost. And what's going to happen is that rugby player is going to be initially moving to the right, collide with the goalpost, so I'll put V initial going to the right, V final going to the left. We know what V initial is. We don't know what V final is, but that's ultimately what we're going to be looking for. We can take a few extra steps here just to be certain that we understand the situation. And we can go so far as to define our system with an interaction diagram. Our interaction diagram will have our player in one of these boxes. Or in one of these bubbles, I should say. We have the post in another bubble. Of course, we have the floor the rugby is supported by. And we have, or I probably should put the word field. And then we have the entire earth below that. When we take a look at this, we have several interactions going on here. We have the entire earth and the player interacting through gravity, the floor, and the player interacting through a normal force. And then I'm going to put this one in orange. The post and the player interacting through this force of 1.76 times 10 to the 4 newtons. We define our system. And when we define our system, we are asking the question, what are we interested in? And if we define our system in a clever way, and of course there are other interactions going on between the floor and the post and nuts, but it's not going to play a huge role in this problem. So when we define our system, we're really concerned with the player in this problem. So we're going to define our system to be the player. Everything outside of this green bubble is the environment. Everything inside the green bubble is the player. Now I'm being specific here because in the next video, when I do some conservation of momentum problems, we're actually going to define our systems a little more carefully. But here we have our player. We draw a free body diagram. Our free body diagram will have the normal force going upwards, the weight going downwards, and the force of the goalpost, I'll put GP on there for force of goalpost, going to the left. And I do this for a very specific reason, because direction matters, and this puts very clearly in our mind the direction of our force. Now, I could have gone here and flipped the script. I could have put the player initially moving to the left and the goalpost pushing to the right. I could have done that, but I didn't. I chose this as my defined directionality, and I need to stick with it at this point. And what this tells us is that our initial velocity we're going to take to be positive, our final velocity is going to be negative because it is to the left, and our force from the goalpost is also going to be to the left. We move on to wonder, okay, well, what are our known values here? Our known values are the mass of the player, the initial velocity, and I know that with those two values I can figure out the initial momentum just like I did in the earlier problems. I can find with the time and the force, I can find the value of impulse, and I know that impulse tells me about changing momentum, so maybe that'll help me. I then ask the question, well, what am I looking for? I'm looking at the final speed and the final velocity. If I wanted to know that, that just includes directionality. But that's my end goal. How am I going to achieve it? Well, I start with impulse is equal to the change in momentum. I start here because I know this is a problem that involves interactions and changes in motion. And since it involves those two things, I will start with the impulse momentum theorem. Well, I know momentum is mass times velocity, and I know that impulse is force times time. I plug those in together with the impulse momentum theorem, combine all three of these, and what I end up with is that the impulse force times time is equal to the change in momentum, or mass times initial velocity, mass times final velocity, minus mass times initial velocity. So you combine those three equations and we arrive at this force times time is equal to mass times final velocity minus mass times initial velocity. The minus because we always take final minus initial to be our deltas. We take a look at this and I say, I know what the force is, I know what the time is, I know what the mass of our player is, and I know what the initial velocity is. So the only unknown here is the final velocity. This is one equation with one unknown. This is definitely solvable. So clearing up those bubbles that I've just drawn, we ask the question, well, how does this solve? We can solve this algebraically first, and I almost always recommend solving things algebraically first just because sometimes it can help us get to a more succinct answer. So here what I'm going to do first is I'm going to divide the mass out from both sides. So we'll take the algebra one step at a time. Force times time divided by mass. So you divide the left side by mass, and that just puts it in a fraction. On the right-hand side, we have mass in both terms. We're dividing out mass. So what that's going to be is final velocity minus your initial velocity. And now we have initial velocity on the right-hand side. We want to move to the left. So what we're going to do is we're going to add v initial to both sides. And that'll arrive at the equation force times time over mass plus your initial velocity is equal to your final velocity. And the tricky part here, again, is to remember directionality. Because that force has a direction, and that direction we put being to the left, meaning it's going to be negative. So when we input our force here, we have to be sure to input that the force is equal to a negative, because it's to the left, 1.76 times 10 to the 4 newtons. And when we have this, just a quick note on the velocity, actually, the initial velocity we want to make sure is going to be positive, and we'll put it in the I hat here. It's one-dimensional, so it's kind of redundant, but we'll put it in the I hat here. And our initial velocity, well, our initial velocity is going to be 8.00 times 10 to the, nope, not times 10 to the 4. Oops. Sorry. Little technical issue there. Okay, so we have 8 times 10. No, not 8 times 10. What am I doing? 0.8 meters per second in the I-hat direction. So you take this, we plug it all in, and what you'll find is that the final velocity is equal to negative 0.8 meters per second. Negative meaning to the left, and that's exactly what we predicted, that the rugby player will be moving to the left. So that gives us our final velocity. So we utilize the impulse momentum theorem here, and this is a utilization where we know what the force is, we know what the time is, we know what the mass is, and the initial velocity. So it's a pretty straightforward application, but we could get more complex problems. We can get complex problems that don't necessarily give you the time, right? We're just told about what the after effects are. So here we're given the problem where a hammer strikes a nail. We're not told how long the impact is because honestly we don't usually know that value. But what we can determine is how far the nail is embedded into the wood board that we're nailing it into. So we start off with, again, drawing a picture. Here is my wood board. Here is my nail. And here is my hammer. Do my best at drawing a hammer. The hammer is going to strike the nail, and what's going to happen is the nail is going to embed itself. I'll use blue here to represent the final. The nail is going to embed itself 1 centimeter into the wood board. We're asked here again about the effects of the force on the nail, and what we know is that the the force is going to cause an impulse, which causes a change in momentum. And we want to solve this by utilizing that impulse momentum theorem, that force times time is equal to the change in momentum, m1 v1 final minus m1 v1 initial. Actually, I don't know. I need to specify 1 there. M times v final minus m times v initial. The same process we had last time, right? But the problem is we don't have time, right? We don't know how long the nail was embedded into the board. How do we figure that out? Well, we can start by analyzing the hammer. We start by looking at the hammer because the hammer will stop in the same amount of time that the nail does. The hammer impacts the nail for as long as the nail impacts the hammer. So we ask, well, how long is the hammer interacting with the nail? And I probably shouldn't use delta here. How long is it interacting with the hammer here? Well, it's interacting with the time v final minus v initial over the acceleration. This is one of our kinematic equations that we've seen earlier. This could tell us how long that it's been impacting the nail for. But again, we raise the question, well, we don't have the acceleration. How are we going to find the acceleration? Another great thing about the impact is that our nail and our hammer, while they are impacting, they are going to be mechanically connected. Since they are mechanically connected, they will share the same motional quantities. That means that the hammer comes to rest in the same amount of time in the same amount of distance that the nail does. So we can take the acceleration to be final velocity squared minus the initial velocity squared divided by 2 times the displacement. I'll put delta y here to represent the vertical displacement, but that delta y is just the 1 centimeter distance. Okay, so that means that when we solve this problem, we can first figure out the acceleration. Once we have the acceleration, we can figure out the time. And once we have the time, we can figure out the force, or the average force here. And what you should find is that the average force, I'm going to leave this as a I'm going to leave this up to you to figure out the full solution here. This gives you most of the way. It's up to you to finish it off. What you should find is that the average force comes out to, when you calculate it out, 1102.5 newtons, 1,102.5 newtons. Of course, that is not the number of sig figs that are present. Here we have 3 sig figs present, so that means 1.10. We have 3 sig figs, and then I'm going to write it in scientific notation where you have times 10 to the 1, 2, 3 newtons. And that is our average force. Go ahead and try that. And I should probably put negative j hat for our direction. Go ahead and try that at home. And if you have any questions, please feel free to ask. Otherwise, I will see you in the next video.